Is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
All right, great. So in the previous class, we had finished the first lesson that was on complex functions. We were discussing about the analyticity of functions, and I had given you this assignment to check whether these functions are analytic or not. I have been told that most of you were able to do everything except the last one, right? I think it was Mafidul. Mafidul, was it you who sent me a text that day? Mafidul is here? No, he's not here. Okay. So were you able to do the last one at least? Anybody? The last one, that is f of z is equal to ln of z. Anyone? I'm talking about this one. F of z equal to ln of z.
Sir, I did that.
Mehul, okay. You did that?
Yes, sir. I took Z
Is this?
as R e to the power I theta as you told.
Yes, correct. That's how you're supposed to do. Okay. Others, did you do that? Mehul, did you find it to be analytic or not?
Yes, sir, it is analytic. Only Z
It is.
conjugate is not analytic. So rest all are
Okay,
analytic.
okay, okay, great. So I don't know because some students had texted me and then they said that they did not do get this. So I just want to show you here how we can go about doing this. The function that you're supposed to check, okay, the function is f of z equals ln of z, and as Mehul had said, this can be written as ln of z. You write it as e to the power r e to the power I theta. Okay, so this is going to give us ln of r plus ln of e to the power I theta, which is going to simply be equal to I theta. So now when we have in this form, okay, we're going to use the polar form, okay, and we'll use the expression for r and theta. So this is how we're going to proceed, okay. So let's say this is a complex number. Okay, so in the complex plane, so this is the number, this is the z. Okay, so this is the complex number z, and this z is equal to ln r plus I theta. So r is this one. So now we can find out what is r. Okay, r is simply equal to under root, r is simply equal to under root x square plus y square. This is your r, and we have this theta. This theta can be obtained as the tan inverse of y by x, because tan theta is equal to y by x, right? So we have y and we have x. Y by x is equal to tan theta, so theta is equal to tan of y by x. So using this, we can write down this function in terms of x and y. So this gives us ln of under root x square plus y square plus I into tan inverse of y by x. Okay, so now we can immediately we can identify, because f of z is supposed to be u, a function of x and y, plus I into v, which is also a function of x and y. So therefore here u is equal to ln of under root x square plus y square, and v is equal to tan inverse of y by x. So now it's just a matter of finding out their partial derivatives. Just find out the partial derivatives of these, which is really straightforward. So dou u by dou x, okay, will be equal to 1 by 2 times 1 by 2 times 1 divided by x square plus y square times 2x, which is going to give us x divided by x square plus y square. In a similar way, because this is symmetric with respect to x and y, dou u by dou y is equal to y divided by x square plus y square. And we could find out dou v by dou x, which is equal to, we can use this formula, d by d, let's say d by dt of tan inverse of d by dt of tan inverse of, let's say t, this is equal to 1 divided by 1 plus t square. We can use this result directly. So 1 by dou v by dou x. So this is going to give us 1 divided by 1 plus y square by x square. If you work this out, y square by x square, and then here we'll have minus y by x square. Okay, so when you simplify this, you'll get this to be equal to minus y divided by x square plus y square. And finally, this is going to give us dou v by dou y. When you work this out, this again will be 1 by 1 plus y square by x square, y square by x square, times, you'll have 1 by x. And when you simplify this, you'll get x divided by x square plus y square. And we immediately find that dou u by dou x is equal to dou v by dou y. Dou u by dou x, this is equal to this, and this is equal to the negative of this. Okay, so the Cauchy-Riemann conditions are satisfied. So if the Cauchy-Riemann conditions are satisfied, this f of this, so therefore the Cauchy-Riemann conditions are satisfied, hence f of z is equal to ln of z. It is analytic, okay, over what region? It is analytic everywhere except for those points where u and v, the partial derivatives, they are not defined. And there is only one point where the partial derivatives u and v are not defined, that is z equals 0. Because when z equals 0, then that's the only place where x and y simultaneously, both of them will become 0. So as a result, the partial derivative dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, all of them will become undefined. So this is analytic everywhere except at z equals 0. Okay, so this is the analysis, checking the analyticity of this function f of z equal to ln z. Okay, so that's about this one. Okay, so now we'll proceed to the next lesson, which is on complex integration. Okay, this is on complex integration. So these are what we will discuss. We will discuss first the complex line integral. What is a complex line integral? Okay, and what are their properties and how to evaluate complex line integrals. Then we'll move on to a very important theorem, which is known as the Cauchy's integral theorem. Okay, and you can apply this Cauchy's integral theorem for many different kind of geometries, and you can get some really interesting result in a very elegant way. You can get the results. Okay, so that's what we're going to do next, and finally we'll arrive at a way of evaluating definite integrals, and that is by a formula, that is by something known as the Cauchy's integral formula, which is, of course, it is based on the Cauchy integral theorem. So first we'll define what is a line integral. Okay, so complex line integrals are definite integrals. So that's the first thing that we need to keep in mind. When you say complex line integrals, we are talking about definite integrals. Okay, and these definite integrals, they are defined on the complex plane. Okay, these definite integrals which are defined on the complex plane, and they are defined in this way. You are integrating f of z dz over some curve c. So c here is a curve. Okay, so the function that you are integrating, that is known as the integrand, and this curve c that we have here, it is known as the path of integration, the path over which you are considering the integration. Because remember, we are talking about, when we say complex integration, this is integration on a plane. Okay, this is integration on a plane. So if it is integration on a plane, what this implies is this is a two-dimensional integration. Okay, this is a two-dimensional integration. Okay, so if you're talking about a two-dimensional integration, then we need to talk about what is the path over which you are carrying out this integration. Okay, so this is one thing that we always need to keep in mind. Okay, so this curve c that we have here, this curve c in the complex plane, this curve c may have a parameterized representation. So we are going to use this term very often. This is called as parameterized representation. Anybody, any idea what exactly is the meaning of this word? What is parameterized representation? Parameterized representation. Any idea? Parameterized representation. Anybody? Mehul, what is a parameterized representation?
Sir, when we relate different variables through some means, we are relating many variables are related to one.
Okay.
Means
Yeah. Okay.
through a
Yeah.
single variable, I am not able to express here. Yes.
Yeah, yeah, I get it. I get what you said. What you said is essentially correct. Okay, when you have different variables, and these different variables you would like to express in terms of one single common variable. Okay, so that common variable is known as a parameter. Okay, and we say that this relationship has been parameterized. So essentially, what we are going to one example that I can give you is it's a physical example. Okay, the example is that of let's say I take, for example, projectile motion. Okay, the motion of a projectile, a stone, when you throw it from the ground and as it proceeds, as it moves. Okay, so that motion is known as projectile motion. So we are having the coordinate axis, we have the x-axis and the y-axis. Okay, so I have an object here. Okay, I have an object here, and this object, you launch it at certain initial velocity. Okay, you launch this object at certain initial velocity. Let's say this initial velocity is u. Okay, we'll launch it at some initial velocity, u. Then what is going to happen is it's going to take a parabolic path, right? It's going to take a parabolic path because of the gravitational force is going to take a parabolic path, and eventually it's going to land somewhere over here. Now let's say at any point over here of this particle, at any point, I want to know what is its position. Okay, I want to know what is its position, that is its instantaneous position. Let's say when the particle is over here, I want to know what is its instantaneous position. In other words, I want to know what is r as a function of t, because this is at t equal to 0, and this is at some time t. This is t equals to whatever is the time of flight. So I want to know in between, at any point wherever the particle is, I would like to know what is its position. So one way that we can do it is this way. That is r of t, r which is a function of time. Now moment, it's a function of time. That means, sorry, moment we're talking about position, that means it will have two coordinates. It will have the x coordinate and the y coordinate. So here we have r is equal to, it'll have an x coordinate. This x coordinate will depend on t, and then we have a y coordinate. This y coordinate will also depend on time. Okay, so if you know this x as a function of t and y as a function of t, then we can find out what is its position at any point of time t. So here in this case, we say that and y are parameterized by t. So x and y are two variables, and these two are parameterized by t. That means as time increases, x and y will also change. Okay, because x and y, they are related to time t, because x and y are related to time t. So we don't need to remember exactly what are the values of x and y. All we need to do is what is the relation that x bears with t, and what is the relation that y bears with t. That's all we need to know. And if we know that, then we can find out what is this t. So in this case, what will be x of t? What will be x of t? And what will be y of t, Mehul?
So x of t is u cos theta into t.
Okay, x is equal to, this is your theta.
Ux u cos theta into t.
Okay, and this one will be equal to
U sin theta into t minus half gt square.
ut sine theta minus
Half gt
half
square.
into g t square. That's all. So you just need to know how this x is changing with t, and you just need to know how y is changing with t. Now all we need to do is just keep on varying this t. So t becomes a parameter. As you change t, the x and y value corresponding will change, and as a result the position of the particle is also going to change. Okay, so this is one example. Okay, you could talk of, there are many other examples are there. Okay, lots of different examples are there. Another example could be something like this. uh, you could think of circular motion. So let's say I have an object which is moving around on a circle. Okay, an object which is moving around on a circular path, so something like this. So we have a particle which is going around on a circular path like this. At any point, let's say the particle is over here. Okay, and it is going around like this in this direction. Okay, it is going around in a circular path. So it is rotating at a constant angular momentum omega. It is rotating at a constant angular momentum omega. So let's say this is the position of the particle. Okay, this is the position of the particle r. So r is a function of time t. So immediately you know that there is going to be a x component. There's going to be an x component here, and there's going to be a y component here, right? And then this angle theta that we have, this theta will be equal to omega into t. This we immediately know. Okay, so now we can write down that x of t, x is a function of time. What is it equal to? X is a function of time. So let's say the total radius, the radius is capital R. Let's say the total radius of this circular path is capital R. So what will be x? X will be simply equal to R into cos theta, and theta is equal to omega t. So x will be equal to R cos omega t, and similarly y of t will be equal to r sine theta, which is equal to r sine omega t. So therefore the position that we're looking for, the position of this, okay, my mistake. Yeah, I had put this as, I should put, if I put this as a vector, r I have considered to be a vector. So if r is a vector, I should put the I cap and the j cap. Okay, so I cap and j cap here. In a similar way, I want this position vector r. So this position vector here, it is going to be equal to I cap into x of t, which is this r cos omega t, plus j cap into y of t, which is r sine omega t. So this gives me the position. So here again, in this case also, x and t. Okay, so x and y, these two are, these are parameterized by this another variable t, another common variable called as t. So this is known as parameterization. So you can parameterize any curve. You see, this is a curve, it's a parabolic curve, this is a circular curve. So any curve we can actually parameterize it like this. Okay, so this is what I mean. So curve C, okay, it can have a parameterized representation, because after all, this is curve C is defined on a plane. So if it's defined on a plane, that means that curve could have x and y components both. And here in this case, of course, x and y, these are the real and the imaginary parts. So I have made a small mistake here. The mistake is there should be I here, okay, I into y of t. Okay, so now C has got a parameterized representation, and the value of C, sorry, value of the parameter T, it lies between A and B, just like here in this case. In the case of the parabolic motion, the value of T, what is the value of T? Value of T lies between 0 and capital T, which is the total time of flight. So this is A and this is B. So the parameter values, right? The parameter, whatever is the parameter, that parameter has got a lower bound and an upper bound. Okay. That parameter has got a lower bound and an upper bound. So this is the lower bound and this is the upper bound, A and B. So this is what we are talking about here. Okay, so now we need to define this because we are talking about moving along a curve. So if you're moving along a curve, then what is the sense in which one direction could be positive, one direction could be negative. So here we need some kind of a convention. The convention is positive sense on C, positive sense on C. That means when you move along a curve, are you moving in the positive direction or the negative direction? Like for instance here, if you're moving along from towards the right side, then you're moving along the positive x direction. If you move towards the left, you're moving in the negative x direction, right? So we have a sense of direction. If you're moving along any direction, we have a sense of, are you moving along the positive x direction or are you moving along the negative direction? Similarly over here, positive and negative sense we define, when you have circular motion, we define as the circular motion, the motion to be positive if you're moving in the anti-clockwise direction, and the motion is supposed to be negative if you're moving in the clockwise direction. So which direction you move, that is going to decide what is the sense of the curve. Okay, whether it's a positive sense of the curve or negative sense of the curve. So that's going to that's going to be defined. Okay, from problem to problem it could vary. In case of complex line integrals, again here also we are talking about a curve. So we could have something like this. We could have the real axis and we could have the imaginary axis, and then we could have a curve like this. Okay, so this is the starting point and this is the end point. So whether you go this way, okay, whether you go this way or you go this way, one direction is positive and one direction is negative. Now how do you choose whether it's positive or negative? The answer is given by whether the t is increasing or not. So if we have something like this at this point, because you see t, its lower bound is a, so if at this point, okay, if at this point t is equal to a, let's say at this point, let's say t is equal to a, t is equal to a at this point, and let's say t is equal to b at this point, then the positive sense of c, this is the curve c, this sense is said to be positive if you're moving in the increasing direction, because a is less than b. If you're going from a to b, if you're going from this point to this point, that is if you're going from point number 1 to point number 2, you're going from t equal to a to t equal to b, that means t is increasing, t is increasing in this case. So this is the positive sense. And in the other direction, from 2 if you come to 1, then you're going from from t equal to b to t equal to a. That means in this case t is decreasing. Okay, t is increasing here and t is decreasing. So this is taken as a negative sense. So positive sense is here and negative sense is here. So this is how we define whether the sense of moving along a particular path, whether it's positive or negative. Okay, and there is a general assumption. The assumption is all paths of integration for complex line integrals are assumed to be piecewise smooth. What do you understand by piecewise smooth? What do you understand by piecewise smooth? Anybody? Piecewise smooth curve. I'll not go into the mathematical definition of this. You would have probably done this in a course on real analysis in your undergraduate. So smooth curve. A smooth curve is that in which the derivative does not change. The derivative does not have any discontinuities. So if a curve like this, over here, if you go from point number 1 to point number 2, you will find that the derivative changes gradually. There is a gradual change in the derivative, right? So here the derivatives at this point is positive, 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 becomes zero somewhere here, and again it becomes negative. So that the derivative, it gradually changes. Okay, so that's a smooth curve. Okay, then a piecewise smooth curve. So this is a smooth curve. A piecewise smooth curve is basically this. A piecewise smooth curve is made up of many other smooth curves. So we have, you start from this point, point number 1, go like this and reach some other point. point number 2. From point number 2, you go like this, and let's say you reach point number 3. From point number 3, you go in a straight line, reach point number 4. From point number 4, again you reach here, point number 5. So this is a piecewise smooth curve. Okay, you can break this down, break this curve into different points. You see point 1, point 2, point 3, point 4, point 5. At all of these points, there is a abrupt change in the, there is a sudden change in the derivative. Here the derivative on this point number 2, for instance, the left side, the derivative is positive. Here the derivative is positive. Right side, suddenly the derivative becomes negative. Okay, again here also the derivative is negative. Suddenly on the right side, the derivative again becomes positive. There is an abrupt change in the value of the derivative. So such curves are known as piecewise smooth curves. Okay, so the general assumption is the path of integration, the path over which we are doing the integration, that path of integration is assumed to be piecewise smooth. At least it must be piecewise smooth. If not completely smooth, at least piecewise smooth. Okay, so these are some of the assumptions that we make, okay, when we are trying to find out the complex line integral. We're going to the next slide. So now what we do is we partition the interval into n subintervals. So like I said, this parameter t that we have, right, the parameter t. Okay, so let's say this is an axis. Okay, this is the axis for the parameter. So we have a here and we have b here. These are the range of values that t will take, okay, to describe that curve. Okay, so what we do is we divide this into n sub intervals. We divide this into n sub intervals. So first interval, second interval, third interval, and so on. And these are n intervals. Okay, so the first one, the very first one, the point A, we call it as t0. Then this point we call it as t1. This point we call it as t2, and so on. This point we call it as tn. That means the point previous to this point will be tn minus 1. So we divided the this one, the interval of the parameter, into total interval of the parameter. We divided into n sub intervals. So here t0 less than t1 less than, and so on, all the way till tn. Okay. So with C being a smooth curve in the complex plane and a continuous function defined at each point, there exists corresponding subdivisions of C. So because I have, taken the parameter and I've divided into n subdivisions, and for each point on this, let's say it's like this, from A to B, the parameter takes the value A to B. At any point, if I take any point between A and B, if I take, let's say, I take a Z here, okay, so sorry, not Z. If let's say I take some value of t, let's say this value of t I have taken. So this value of t, what will it do is it will correspond to some value z on the complex plane. Okay, real and imaginary. I'll show you in the form of a diagram. Okay, next slide itself. So for each and every value, this point is going to correspond to a z on the complex plane. Okay, so it means for each and every points on both sides of the sub intervals. Okay, so t0, t1, t2. So correspondingly, t0 is going to correspond to a point z0. T1 is going to correspond to a point z1. T2 is going to correspond to a point z2, and so on, all the way till n. Okay. So this is how it proceeds. Okay, I'll show you. So here, this is the parameter. Now remember, when I say parameter, this parameter t, it is always a real number. Okay, the parameter cannot be complex. Okay, this parameter, when I say that the curve has been parameterized, by some parameter t, we mean that this t is always a real number. T cannot be a complex number. Okay, because it's real, that's why we are able to identify this t on the on a number line like this. Okay, so 1 second. Yeah, so we have this axis of the parameters. This is the axis of the parameter, that is t takes these values here. So this is the starting value a, and this is the ending value, which is b. corresponding to starting value, we have t0, like I showed some time back. We have divided it into n subintervals, so first interval, second interval, and so on. This is the nth interval. Okay, so over here, this point I'll call it as t1, this point I'll call it as t2, and so on, and this point is your tn. Now, like I said, this is a parameter. Every value of t is going to correspond to a z value here. So moment I take t naught here, the moment I take t naught here, moment I take this parameter t naught here, this value, then what is going to happen is, just because it's parameterized, it's going to correspond to this point z naught. Similarly, if I take the t1 value, this t1 is going to give me a point which is z1. I take t2 is going to give me a value z2. Okay, and so on. Tn minus 1, it is going to give me a point zn minus 1, and tn, which is b, which is going to give me a point zn. So for all of these points on the subintervals, we have corresponding points on the complex plane. So as you move along this real axis, as you move from a to b, as you move from a to b on the complex plane, you're moving from z0 to zn. So this is the whole idea of parameterization. Is this clear to everyone? Anybody, if you have a question, it's better to get clarified right now. If you have any questions, please get them clarified right now. Anybody? Can I proceed? Can I proceed?
Yes, sir.
Yes,
Okay, great.
sir.
Okay. So now, remember in the previous class, I had shown you this, the previous class, I had shown you this diagram, right, of complex functions. Let me just pull up the diagram again. The mapping of complex functions. Yeah, here, you see, remember this? What is a complex function? We have a set of values z, and in another complex plane, we have a set of values w. We said that w is a function, w is equal to f of z. W is a function of z. So when you go on this plane, you're actually going in this plane. So for each point on this blue colored domain, there is going to be a corresponding point on this pink colored domain. Okay, so this is basically a function. Okay, is this clear? This point. So every point z will correspond to a point over here. Okay, so taking this idea forward.
Yes,
Yeah.
sir.
So taking this idea forward, let's now proceed and bring this here. Now here, every point over here, because we are talking about some function. We're talking about some function. This here, this is z. Okay, this gives me z values. This gives me function of z values. Then for every z, there is going to be a corresponding value over here. So if I take z naught, this is going to correspond to, because there is a function which is defined, that function is going to take a value f of z naught. Similarly, z1, that is going to give me a value, can take a value f of z1. z2, it is going to give me a value f of z2, and so on. Z minus 1 is going to give me a value here. And finally, zn, when you apply this to a function, it is going to give me a value f of zn. So this is basically what happens here. So you are changing only this parameter, changing only t. When you change t, accordingly z changes. And when z changes, then the value of the function also is going to change. Fine. So this is what we mean by parameterization of a function. Okay, parameterization of the variable, the independent variable of a function. All right. So now let's take a small part of this one. Okay, let's take one small part, like for example, this point. Okay. So on this curve on the z plane, let's say I take a small part like this. Let's say I take a small span of this. Let's say this part, only this part. Okay. I take only this part, and we're going to look at this more closely. Okay, we're going to look at only this part. Okay, so one end of this, I'll call it as zk minus 1. Then this point must be zk, because you see how we have divided this, how we had made this, this interval, right? The interval of the parameters, no? How we had made this interval we made the interval like this. So we had, this was the axis of the parameter t. So we had here t0, and at the end we had tn. Let's say I take 2 points, okay, 1 point and another point. Let's say this point is tk, okay. Then this point, the previous point, it must be equal to tk minus 1, okay. Now this tk minus 1, because it's a parameter, it will correspond to, it will correspond to some point zk minus 1, and this is going to correspond to some other point, that is zk. Okay, so now between these two, again there is a curve here. So from zk minus 1 to zk, here in between I'll take some point here. Okay, but I'll not call this point as z. Okay, I'll not call this point as z, because z is the samples that I'm taking here. Z are the samples that I'm taking on the curve. Like you can see here, z are the samples that we are taking on the curve. So between any two samples, z2 and z3 and z4, between any two such samples, I define a new variable. I define a new variable. Okay, this one. How do you spell this? This is a Greek letter. How do you spell this? This is spelled as zeta. Okay, this is a Greek letter zeta. So we have a variable here from zk minus 1 to zk, only for this small part, only for the small small segment of the curve, only for the small. Remember, this is a part of C. Okay, this entire thing that we see here, this is a part of C. So we are basically dividing the C into, we are taking a small segment of the C. So only for the small segment I introduce a new dummy variable. That dummy variable is zeta. Okay, now corresponding to this dummy variable on the other side, on the other Argon diagram, there is going to be the function, the value of the function. So what is function? That value of the function is simply, or you have to just put as the argument, you have to put whatever is a complex number. The complex number is, let's say, zeta k. Okay, and this zeta k, the value of the function will be f of zeta k. Okay, so this is what we have here. So now what we do is, let me clear this up. So we take the kth subdivision. This is a kth subdivision. Kth subdivision will go from zk minus 1 to zk. So this is the kth subdivision. Okay, so we choose an arbitrary point. We choose an arbitrary point. This is an arbitrary point, zeta k. And this zeta k lies between zk minus 1 and zk on C. So now remember, this is going to be a part of the curve C. Okay, so that means zeta k is equal to z of t. Remember, we are still parameterizing it. We're still parameterizing it. Only thing is, now the range of values is going to change. The range of values of the parameter is going to change for this zeta k. For the entire curve, let's say this is the curve. Okay, this is the entire curve. This is the entire curve C. For the entire curve C, this point t corresponds to A, and this point t corresponds to B. But I'm taking a small part of this. Okay, I'm taking a small part of this. This point is zk minus 1, and this point is zk. So this is going to correspond to tk minus 1, and this is going to correspond to tk. So now how, for the entire curve, the range of values for entire curve, the range of values of the parameter, it lies between A and B. In a similar way, for the segment, okay, for the segment, that is zeta k, the value of the parameter, it is not going to lie between A and B. It is going to lie between this value, that is tk minus 1, and this value, which is tk. Okay, so that's why we write it like this. The value of the parameter is going to lie between tk minus 1 and tk. Okay, so now we are going to form a sum. Okay, a small sum. What is that sum? All we need to do is take the kth subdivision. This is the kth subdivision, and in this kth subdivision, what you do is you take, let's say, a point somewhere in the middle. That point I'll call it as zeta k. Okay, and this zeta k, the corresponding value of the function will be f of zeta k. This function value, okay, this function value Let me use a different color. Okay, so this function value and this interval, okay, the range of this interval, you multiply these two. Okay, you multiply these two. For this subinterval, we are going to get a product, that is f of zeta k into delta zk. Then there is going to be the other interval, next interval, there's going to be a next interval. So for the next interval also you do the same thing. For the previous interval also you do the same thing. Okay, so for each and every of these intervals, for each and every of these segments on the curve, you find out f of zeta k, multiply this with delta zk, and then you take the sum of all of them, take the sum of this over the entire curve, take the sum of this over the entire curve. So essentially what you're doing is, so let's say this is the entire curve, this is the entire curve C, this is one end, this is the other end. So you divide this into many small segments, you divide this into many small segments. So the first segment you'll have f of zeta 1 into delta z1. For the second segment, f of zeta 2 into delta z2. Same thing for the third segment. Okay, for the third segment, in a similar way, f of zeta 3 delta z3, and so on. The last segment, this is going to be equal to f of zeta n delta zn. Okay, you'll get each of these products will give you some value. So now what you do is you just add this one plus this one plus this one and so on all the way till this. This is the sum. This Sn is the sum. So this is the sum that we form. Okay, by taking each of these products and adding them together, this is the sum that we form. Okay, I'll erase this. Okay, so now in this sum, as n tends towards infinity, in this sum, as n tends towards infinity, what do you understand by n tending towards infinity? This upper limit is n, right? It's you're taking summation of k goes from 1 to n. What do you understand by the this one, n tending towards infinity? Anyone? N tending towards infinity. What do you understand by this? Let's go back and see what is this n. What is this n? What is n? N is the number of subintervals. That means n is simply how many intervals have you made on the parameter, right? On the range of parameters. So if n goes towards infinity, what will happen? So let's say this is the curve. This is a curve. This is from A to B. Let's say n is equal to 2. That means you have taken only 2 divisions. N equal to 4, you have taken 4 divisions. N equal to 8, you have taken 8 divisions, 8 intervals. N equal to 16, that means you have divided into 16 parts. So as n increases, what's happening? As n increases, what's happening? The size of these segments are getting smaller and smaller, right? So this is what it means. So when you take the limit as n tends towards infinity, this difference tk minus tk minus 1, tk minus tk minus 1, this will tend towards 0. And delta zk will also tend towards 0, because this interval, they're getting closer and closer. You're making even smaller, more number of divisions. You're taking smaller and smaller subdivisions. You take smaller and smaller subdivisions, that means this delta zk, this will tend towards 0. Modulus of course, this intercenter distance, this will tend towards 0. Okay, so when that happens, this sum that we are talking about, this sum, we are taking that sum, this sum becomes something called as the line integral. Okay, so we take finite number of such intervals and we add this sum. Okay, f of zeta k into delta zk, we add this. N is finite. But now if you make n infinity, then in that limit, as n tends towards infinity, this sum that we have here, this sum takes a value, and that is value is known as the line integral of this function over the curve C. So line integral is basically this limit of a finite sum. Line integral is as expected, because integration is basically limit of a sum, right? So in the infinite case, that summation becomes a integration. So that's exactly the same thing that is happening here. So this is the definition of a complex line integral. Is that clear? Is this clear? Any questions? Okay, so now let's just proceed with this. I'll just finish with this next slide. Okay. So this is the definition of a complex line integral. Okay. So now, again, going back to the sum. Okay, the sum that we have, Sn is equal to this one. So now let us say this f is written as u, as a sum of two parts. One part is purely real, another part is purely imaginary. U is purely real and v is purely imaginary. So f of z is written in this way. Now this zeta can be written, you see, because after all, what is this zeta? This is a curve, no? This is, let me show you here. So let's say this is a complex plane. This is a complex plane, real part of z, and this is the imaginary part of z. Okay, so on this plane we have a curve. Okay, we have a curve. That curve is C. Now here what we do is we divide this into small segments. In this segment, okay, in this segment there is a point. That point is your zeta, right? That point is your zeta k, right? Now, but this zeta k is, after all, it is a point on the complex plane, so it will be basically a complex number only. Yes or no? Zeta k, it's a point on the complex plane, so it's a complex number only. So if it's a complex number, then it will have a real part and it will have an imaginary part, right? This real part of this zeta k, let us say I call it as eta. Real part, I'll call it as eta k, and this is not this is called psi. This is known as xi. Okay, this is zeta. This is xi, xi, and this is eta. Okay, so here we have eta. Okay, so zeta k will have a real part and will have an imaginary part. The real part I call it as xi k, and the imaginary part I call it as eta k. So as a result, this zeta k can be written as xi k plus I into eta k, and that's what I have done over here. Is that clear? Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay. Next, yeah. Next thing is we have this curve, right? I'll just exaggerate this here. This is z k minus 1, and this is z k. Now this, right? This is your delta zk, right? This is your delta zk. Now this delta zk will also have, okay, let me just write this here. This is your delta zk. This is delta zk. Now this delta zk will have a real part and an imaginary part. So this is the real part, okay, and this is the imaginary part. Okay, so this real part is your delta xk, and this imaginary part is delta yk. So it means your delta zk can be written as real part delta xk plus the imaginary part I into delta yk. Okay, so that's what we have done here. The function, this function f, we are writing in terms of u and v. Okay, this variable, this dummy variable zeta k, we are writing in terms of xi and eta, and this change in the complex number, this change, okay, we are writing in terms of delta xk and delta yk. Okay, because all few of them are complex, so that's why we are writing it like this. Okay, so this is what we get so far. So now all we need to do is just write this back in equation number 3. In equation number 3, we write it like this. So f is written as u plus iv. F is equal to u plus iv, and delta zk is equal to delta xk plus delta yk. Now here u is a function of x and y. U is a function of x and y. That means x and y, I'm replacing it with xi and eta. Similarly here also, v is a function of x and y. X I am replacing because we are considering zeta. Okay, so x I will replace with psi, and y I will replace with eta. So as a result, earlier we used to write it as u of x comma y. Now it will become u of xi comma eta, v of xi comma eta. So this is what we have. Okay, so as a result, when you make this here, now we'll get four sums, because when you open this up, this into this, when you open this up, so u into delta xk will give us one sum. Then we have v into delta yk. V into delta yk, there is a I square, which is going to give us a minus sign. So v into delta yk, another summation. Then u into I delta yk, so that is going to give us u into delta yk. I will take it outside, and finally I into v into delta xk, v into delta xk, that I again goes outside, so we take it common here. So we'll get four summations here. From equation number 5, we get these four sums. Okay, now going back to this, so we have equation number 4, and this we call as equation number 6. So now all we need to do is just take the limit, because you see, after all, what is this Sn? What is this Sn? This is a sum, right? This is a finite sum. And if you take integration, right, as if you take the integral of this one, that means you are taking as sorry, not integration, as limit as n tends towards infinity of Sn. This is nothing but the line integral of the function over C. So you take the limit on this equation number 6, you take the limit on both sides. So left hand side, this is directly going to become the line integral of the function. Right hand side, of course, this one will be integration of u with respect to x. This will be integration of v with respect to y, and this is going to be integration of u with respect to y, and this will be integration of v with respect to x. Okay, because we have assumed here that f, u, and v, they are continuous. Because of that assumption, we are able to write this equation number 6 in terms of this. So line integral you can actually find out use in terms of by integrating u and v in terms of x and y. Okay. Okay, so properties, we'll do it in the next class. Maybe in the next class, we'll do some examples, some problems we will do. Okay, I'll show you how to apply this formula to evaluate the line integral. And then we will study some of the properties of these complex line integrals. Okay, so any questions? Any questions? Okay, so if there are no questions, then I think we can stop for today.